In this class, we'll be looking at how we can leverage Houdini's powerful digital assets to create custom nodes. Before we dive in, what exactly are digital assets? Houdini digital assets, or HDAs for short, are custom node types built out of other nodes. To create them, we build a node network and then promote whatever parameters we think our users might need to change to the node's interface. Our HDA is then saved to a file on disk, creating what we call an operator type library, or OTL for short. Operator type libraries can contain multiple digital assets, but because doing this makes it difficult to track the various node types on disk, the practice is so uncommon that most people use the terms HDA and OTL interchangeably. Once the OTL is saved to disk, it represents a node definition that can then be instantiated into scenes. This is sort of like copying your node network a bunch of times, with a crucial difference. When we update the definition on disk, all of the instances also update. You might think of the definition like a recipe that Houdini follows when it cooks our custom node. If we update the recipe, Houdini will follow the new one we just created. This is a powerful way to build tools in Houdini to solve common problems. Let's try it out by building a node network that makes an emitter from an animated shot camera and see how we can turn it into a reproducible tool. Alright, so we have our starter scene here, which includes two cameras representing two different shots. The first shot we can see has a camera which doesn't rotate too much, it just kind of pans over to look at our little cliff face here. And our second camera contains a much more intense rotation so that we can turn to look at our submarine here. So what our goal is to create an emission surface that will always be present no matter which direction the camera is looking. So in other words, as the camera rotates, we want to have emission surface already there when it turns to look at the submarine. The reason for this is that when we grow tentacles out of our emission surface, we don't want the tentacles to just pop in, and that's what would happen if we just had the emission surface move with the camera. So instead, we're going to have it just be built already, and that way the tentacles will already be there when the camera turns to look at the submarine. Now I've gone ahead and created a network that does this, and the reason for that is that we want to focus this video as much as possible on OTLs. So we'll just take a quick run through the network and see how it works. If I just turn it on really fast, we can see that it builds a nice emission surface. And critically, if we go ahead and plug the first input into the second camera, we can see that it automatically updates with the second camera's motion. When designing node networks that are going to be made into OTLs, it's really important to make them as procedural as possible, because OTLs are really designed to be used in such a way that they are as shot and hip file independent as possible. So what we're going to do is plan the inputs to our system and have our system just work based on those inputs. Now you'll notice that we're using a subnet here, and that subnet contains several geometry nodes. Now, you can actually make OTLs directly out of geometry nodes, but we're not going to be doing that in this class. It's by no means wrong, but I tend to prefer using subnets because it's a little bit more flexible. If you use a geometry node, you can't have other objects inside it because it just is itself an object. If it turns out that you do actually need another object, for example, you need to manipulate object level transforms somehow, it's a little bit awkward to then take your OTL and turn it into a subnet-based OTL. And really, there's no reason not to just use a subnet OTL. In addition, we'll be creating a convention in this class, and indeed enforcing it. And that convention requires us to use subnetworks. All right, so let's just take a quick look at how this system works, and then we'll make it into an OTL. So I'm just going to dive inside, and we can see that we create a camera point here. And all this camera point is if I just set the display flag and turn on normal display, it's just a point that moves and rotates with whatever camera is plugged into it. Now you might be wondering why we need to create our own version of this when, if we just dive inside one of the cameras, there is a cam origin point here. The reason is because SideEffects was not kind enough to provide us with a vector representing which direction the camera is pointing. So we have to do it ourselves. Fortunately, it's quite simple. We just grab the transform from the camera and plug it into our geometry node, and just make a normal that points along the negative z-axis and let Houdini transform it for us. Then we just create a geometry node that doesn't have any transforms on it, and we object merge our camera point with transform set to into this object. And if I just bring up the spreadsheet here, you can see that it's transformed my normal. The nice thing about this is that we can then modify it in world space. So we're just going to remove the Y component of it because we don't want to pick up any weird transforms if the camera rotates up and down. If we did do that, then we might end up having an emission surface that's like way down here. And if it just rotates, it's a little bit easier to see, like way down here. And that might make the camera see the roots of some tentacles. We'll just go ahead and trail to create a line of points for the path of the camera. And you'll notice that our normals are going to represent which direction the camera was pointing on each point. And then we time shift to the end frame to just make sure that we have the entire path of the camera represented by our points. Then we can do a copy to points node, and we're just going to copy our grid. I'm just going to turn off normal display for now because it's not useful anymore. Now, note the way that we're controlling this is by looking at our grid here and just using where the grid is located along its local space before it gets copied to move it out away from the camera. So for example, if we need our emitter to be farther away from the camera, we can just use the center of the grid along the z-axis before it gets copied. I'll just move it like that to push it further away. This will become important later when we start thinking about how to build the interface of our OTL. Then we simply flatten our emission surface by putting it at the top of the bounding box. Use triangulate 2D to turn it all into a single mesh. And since it's a fairly messy mesh, we might worry that when we scatter points to create our tentacles, it might do some weird things with point density with these really small polygons that we've created. So we're just going to use a divide SOP with remove shared edges on to turn it into a single polygon. We'll just go to wireframe mode to show that it's a single polygon. And there's just an output node. Now before we move on, I just want to mention that when we grab the camera point, we are using a relative node path, and this is extremely important. When we're making OTLs and referencing objects inside our OTL, we want to use relative paths. And the reason for this is that we're going to be putting our OTL down inside various HIP files, maybe inside subnets. Maybe we're going to rename our subnet later. And if we're using an absolute path, that will get easily broken. So we want to use relative paths for anything that's inside our OTL. If we're referencing something outside the OTL, we need to use expressions to do that. And we'll be looking at how to do that later in this class. Now, the last thing we've done is just created an output node for our geometry. And the reason for this is that we are going to be using some expressions to grab our emitter and put it into another OTL. It's good to create a convention like this so that it's easy for people to follow. Just going to turn off my camera point and turn on the output, and that's our emitter. All right, so we can imagine a situation where we have our 2-shot cameras, and maybe we're actually working on like 40 shots, and we need to put tentacles into all of them. And we have our nice emitter subnet that we just plug a camera into it and it builds a nice emitter. So we might think, well, we can just go ahead and plug that into our camera and just copy paste it for all 40 shots, and it will go ahead and make our emitters, and maybe we have more subnets that make the actual tentacles that we can also copy paste. And we'll get like a nice version out of all of those subnets. But then maybe we realize that, oops, in this shot, the emitter is just slightly too close to the camera, so we need to push it a little bit further back. And maybe in this shot, it's too far back, so we need to pull it forward. And we realize that this is something that we're doing a lot, like moving the emitter forward and backward. And the problem is that whenever we want to move the emitter in that way, we have to dive inside these subnets and find where to change it. And in this case, it's a fairly simple network, so it's not that hard to find. But if you can imagine a network that has thousands of nodes in it, it could be a bit of a hassle. In addition, we might imagine that we're handing off our tentacle setup to someone who isn't familiar with it, and we want them to be able to just change the emitter distance. Now they have to go through and figure out how the setup works in order to do something really simple like that. So we might think, oh, okay, well, in that case, we'll just make a spare parameter and put it on the subnets interface, and then do channel referencing, and that will make it easy for someone to pick up our setup, which is a really good instinct, and it's actually quite similar to what we're going to actually be doing. But the only problem with that is, since this is just a copy-pasted subnet, what we'll end up having to do is go to all 40 of those shots and add that parameter to all of them, which, if you can imagine, would be quite a big hassle. And if we imagine this sort of thing happens a lot, where we find something that we need to be able to control in that way, it adds up to a lot of lost time. Fortunately, this is where digital assets come in, and it makes this sort of thing a lot easier. So I'm just going to go ahead and delete this subnet. And let's right-click on our subnet and say Create Digital Asset. Now, recall that Houdini differentiates between type names and labels. Label is what name the operator is going to have in the tab menu. And yes, we are creating a whole new node type, which means that it is going to show up in the tab menu, and we can put it down just like any other node. The operator name is the actual type name of the node, which is what Houdini is going to use to, among other things, decide what the default name of the node is going to be. And we'll see how that works when we put it down through the tab menu. First, I'm just going to go ahead and delete my username from the operator name, because OTLs don't really need that kind of credit. And I'm also going to add a version number. Just call it v01. And I'm going to put a space afterwards to add this little underscore here. And the reason for that is, if you imagine that I'm going to put down a new node, it's going to add a 1 or 2 or 3, depending on what other nodes there are in the network editor at the time. And I don't want it to say underscore v011, or like it looks like it's going to be v11. So this underscore just anticipates that Houdini is going to add a 1 there when we put down a new node of this type. And we want it to say something like v01 underscore 1. Now, Houdini does have a specific naming convention that's different from this one that it wants us to use. However, there are some interesting techniques that we can look at surrounding that naming convention that really deserve a video all to itself. So for now, we're just going to be using this convention where it just ends with an underscore. Now, if you recall from the beginning of the video, we said that OTL definitions are saved to files on disk, and once we update those files, it'll update everything. So I'm just going to choose a place for this OTL to live. Now, this is the Edit Operator Type Properties dialog. This is the dialog that we're going to be using to modify our OTL for the most part. But before we do that, let's take a look at how OTLs work in the network editor, now that we've created one. So I'm just going to go ahead and hit accept to close the dialog. And let's try it out. Let's see. We have, in a tab menu, we theoretically should be able to say create emitter. And there it is, create emitter v01. I noticed that we got our nice v01 underscore 1 naming, like I said when we created it, so we don't get the ugly v011 kind of thing. And if we plug it into our other camera, we get our nice other emitter for that camera. So one thing to notice about the difference between these two nodes is that one has this little red unlock icon here, and the other one has a locked icon here. And what that means is that this node is automatically following whatever's on disk, and this node is currently being edited and therefore is not following what's on disk. Now, that's only partly true. In reality, it's only saying I'm not going to follow what's on disk for whatever is inside the node. So, for example, the node network inside the node. But if you change things in that edit type properties dialog, it will still pick it up, which can be a bit confusing and a bit of a gotcha. But the thing to notice here is that for locked nodes, if I double click on it, you can see that all of the parameters are grayed out, and I can't, for example, hit the delete key because this node is following what's on disk. If we come back out, so what if we have this unlocked node and we want to tell it to follow what's on disk? Well, we can right click on it and say match current definition. And you'll notice that the red unlock turned to a lock, and if we double click on it, everything's grayed out on the side. And that means that if we change something on disk, it's going to update this node. If we then want to make further changes, which in this case we do, we're going to right click and just say allow editing of contents. And that means that we can go ahead and make changes inside here. The interesting thing about this as well is that with unlocked nodes, the contents of the node are actually saved into the HIP file. So if you were to save your Houdini session, close it, change what's on disk from another Houdini session, and then reopen this Houdini session, you would keep all of your changes until you tell this node to match current definition. That's the other gotcha about these OTLs, is that if we go in here and change something, let's say I add a null for no reason, and then come back out and say match current definition, it's going to, without warning, just drop all of the changes I have inside. So one thing that's a good thing to get into the habit of, if I just allow editing contents again really quickly, is before you hit match current definition, you always hit save node type. And that just means it's going to save whatever changes you've made. And when you match, it's not actually going to change anything inside. Unless, of course, you want to ditch all those changes, in which case, more power to you. All right, so if we want to look at how to promote our distance from camera parameter, let's just go to our type properties dialog again. We can just right-click on the node and bring up type properties. So we'll be looking at most of these tabs later in the course, but for now, let's just stay focused on how to promote our parameter. So this looks awfully similar to the interface that we use to create spare parameters. And it really is. The biggest difference is that the parameters that we create from the type properties dialog are going to go into the node's definition, whereas spare parameters only affect the one instance of the node that we are currently working on. Now, also notice that Houdini very helpfully kept around all of these parameters that relate to subnets. And the reason for that is that things like translate, rotate, and scale are required for all object level nodes, because Houdini likes to be able to handle object level transforms. So we're not going to actually allow our users to change those things for this node, because this node is based on the camera's transform, and it already knows what to do with that. So what we're going to do is just hide all of them by selecting all of these parameters and saying invisible. Now if I hit apply, notice that it's asking if I want to unlock and save my node, and it's just sort of a shortcut to the same operation that we did by right-clicking and saying allow editing of contents. So if we say unlock and save, the other thing to be aware of is that every time you hit apply or accept here, it's actually going to update the node's definition on disk. This means that if we have gone inside of our OTL and added a node, let's just do that now, and then we hit apply here, it will actually update the node's definition. So we would expect if we dive inside this node, we would see our null, and in fact we do. I don't actually want a null in there, so I'm going to just go ahead and delete it and hit apply again. So let's go ahead and create our distance from camera parameter. And I'm going to give the default something like 40, which is pretty close to the value we're already using. And hit apply, and we can see that it appeared here. And now we can just dive inside and do the same thing that we normally do with spare parameters by making a channel reference. Distance from camera. Yes. But the cool thing is that once we right click and say save node type, now those changes have occurred over here. So instead of having to go through and hook it up again, we can just say, oh, my distance from camera already works. And you can imagine if you had 40 HIP files with 40 emitters and 40 different cameras, this sort of thing would speed things up a lot if you need to make changes like that. So that was kind of a really quick tour. So let's just do the same thing with another parameters. I'm going to right click, I'm going to say go to type properties. I'm in my parameters pane here in type properties, and remember we have to do it from type properties and not from the gear here that says edit parameter interface, because that's going to make spare parameters and those will not be part of the node's definition. Now we can dive inside here and find another parameter to promote, but let's say that what I want here is the size of each grid that we're copying to the points. What I can do is just go to the From Nodes tab and just expand it out. Find my grid node and just drag the size in. And let's just call it grid size. Hit apply. And now since we've already hit apply, I'm just going to hit cancel just to get rid of the dialog. Now we can already go to our other OTL and change the grid size. In this video, we looked briefly at how to create a nice emitter from our camera. And then we looked at how to create an OTL out of it and leverage the power of OTLs across multiple shots.